Hello everyone, welcome to all in this lecture. So in this lecture I am going to discuss design of solar foundation. So design of solar foundation, it means we are going to calculate or we are going to find the dimension of the footing. Like we are going to find what is the width, what will be the width of the footing, what will be the length of the footing, and what will be the depth of the footing. So we are going to design the foundation only for the geotechnical point of view, right? It means we are not going to design concrete. We are not going to calculate what are the amount of reinforcement we should be reinforced in the concrete. So we are not going to design the reinforcement concrete. We are just going to find, or we are going to calculate what will be the depth, width, and length of the footing according to by taking care of factor of safety by keep some factor of safety, like the whatever the pressure, whatever the contact pressure, it will come at the base of the footing. It should be always less than the bearing capacity of soil. Otherwise, it would be fail. And that bearing capacity of soil already we have calculated in the previous lecture. We have seen the various method to calculate the bearing capacity of soil. So there are the other method also, like plate load test, that I will discuss in this coming lecture. In the coming lecture, I will discuss the plate load test and some other method also. So suppose you have the bearing capacity of soil for a particular soil. So on the basis of that, you can select or you can design what would be the length, width, and depth of the foundation, right? So types of solar foundation. So foundation basically is the lower part of the column or wall which they support, or we can also define the foundation is the connecting link between the structure to the ground. So basically the main purpose of the foundation, to whatever the load coming on the column and wall, it should be distributed over the large area, so that when it will distribute over the large area, so that whatever the contact pressure will come at the base of the footing, that will be less, right? You will force, what is the force? What is the pressure? The force by area. If you're increasing the area, automatically the pressure will reduce. So that's by doing this process, we can keep lesser value of the contact pressure as compared to the bearing capacity of soil. So the structure can be safe, right? So footing, there are two types of footing I have discussed: shallow foundation and deep foundation. So according to Tarjagi, if the depth of foundation to the ratio of width of the footing is the ratio is less than equal to 1, is df by b is less than equal to 1, so we can call a shallow foundation. Shallow foundation, it means the whatever the foundation, it will be for a shallow depth. It will be a lesser depth, right? So you will see, like in the case of deep foundation, that you will see the depth of foundation to the base ratio would be greater than 1, obviously. So there is also a moderately deep foundation or deep foundation. So shallow foundation basically is required for load bearing wall, or for the wall. In the case of residential places, you will see there is a shallow foundation. So it means if the bearing capacity of soil is relatively higher, so in that case we can go for the shallow foundation. But in other cases also, where the load coming on the wall and column is very less or very lesser value, so that can be suitable. That can be you can get the bearing capacity for the shallow depth for that load, right? I get your point. So that in that cases also we can go for the shallow foundation, right? So there are various types of shallow foundation that I will discuss one by one. The first one is strip footing or continuous footing. Strip footing or continuous footing. So strip footing basically we designed for a load bearing wall, or in other case also where the number of column is placed in one line, and their footing is nearly touched to each other, or they are overlapping. Their footing are overlapping. So in case of when we are go for the isolated footing, so it's better to go for the strip footing. So what we do, suppose a column, so we are provided a footing with a larger cross section just below the wall. In the case of column also, when the column are placed in a single row, so we go for the strip footing. So we provided the some footing with a larger cross section area, so that will distribute over the pressure, the load distribute over the larger area. So in the figure you can see there is a load bearing wall. The cross section is also given. The second one where the row of column is given, a number of column is placed in a single line. Their cross section is also given. So their footing can be a different shape, like inverted T. There is a wall and column, and there is inverted T. Again, the second figure, there is a T shape, or second one is the wide strip. So wide strip is also important. Like, see, all this what I am going to discuss, it depends upon the various projects, like what load are coming in, what are the soil, what type of soil are there, what is their bearing capacity of soil. So all there are many various factors which is very important, and according to on the basis of that we design for different type of footing. So in the figure you can see there is a strip footing is there placed. So what we do, just construct a column over there. In the second figure, you can see there is a number of columns placed in a single line. So we have designed a strip footing, and that's more economical as compared to, suppose you have there is a number of columns placed in a single line, and you are designing a isolated footing. So it's better to design a strip footing. It will be economical, right? Or there are other advantage also, like differential settlement, all those things. So there is other advantage also. So better provide a strip footing. That is more economical as compared to the we are designing for isolated footing for a number of columns. Second one is the split footing or isolated footing. Isolated footing we design to support the individual column or wall, individual column. So what we do, suppose you can see in the figure, there are various types of isolated footing. It can be a different shape. It can be for square footing, it can be for rectangular footing, or it can be for circular footing. So it's also, you can see in this figure that in the third one you will see this is called the step split footing or step isolated footing. So you can see that the third one is a circular in shape, and their dimension is changing. So the bottom one with a larger diameter, the second one is there's some lesser diameter as compared to the bottom one, and then next one column. So what we do, we have not directly provided the fix the diameter which is fixed at the bottom. So we just do the stepping. So that will it will avoid the punching shear. We'll see in the coming lecture what is the punching shear. So that will avoid, and it's better. So that is called the step isolated footing. In the second or in the first case also we will see that whatever the cross section of column, whatever the cross section of footing is larger with the column, so the whatever the load is coming, it will be distributed over the larger area, right? See in the next figure, I have shown a reinforcement detailing of isolated footing. So that is not same for always. Like I have shown for example, like we will see that how detailing are doing. Okay, so you can get some idea like how we are placing. We'll see that whatever the reinforcement place at the bottom is at the bottom. So it cannot be like whatever the cantilever portion, there is T shape and the cantilever portion is coming. So tension will be developed at the bottom side. So we have to reinforce at the bottom. So wherever you will see in the concrete, when the tension is coming, wherever the tension is coming, so we have to reinforce there only. We have to place a steel bar at that place, so that steel bar will take the tension, because obviously concrete is weak to take the tension, and stresses. Next one is the combined footing. Combined footing is required, or we design the combined footing when we have to support the two columns. For example, the two columns, their footing are overlap, and they are nearly each other, like very close to each other. Okay, so we go for the combined footing. See in the figure. But a combined footing can be in rectangular shape or can be in the trapezoidal shape. So in the why we are going for design the trapezoidal footing, there are the two places we have to go for the trapezoidal combined footing. First, suppose in the two columns the loads are coming on the two columns which we are going to combine, and that are different. So to making the contact pressure is equal throughout the footing, we have to increase the area on the larger load side with the larger load which are coming on the second column or first column, wherever is coming. So we have to increase area below that. We have to increase the distributing area just below the column. So by doing that, we have to go for the trapezoidal combined footing. In other cases also where you will see, like it's very rare, but you will see that suppose that soil bearing capacity is varying throughout the footing. So according to that also we have to we have to go for the trapezoidal combined footing. So by designing the trapezoidal combined footing, we can make contact pressure equal throughout the base of the footing, right? Or in other cases, so that's very important. Suppose one column is touching the property line. So touching the property line, it means the footing cannot be moved outward from the property line. So in that case, what we'll do? So what we do, we just increase the width on the property line, on the side of property line. So it will be, the area will be increased and the contact pressure, we can make it equal throughout the footing, throughout the base of the footing. So in that case also, when one column is touching to the property line, so in that case also we can go for the trapezoidal combined footing. In the figure you can see there is a combined footing is shown with the rectangle. This is the rectangular combined footing. So rectangular combined footing generally is designed. Generally we design for when the same load are coming on the two columns. So in that case we go for the rectangular combined footing. You can see the reinforcement detailing for the combined footing. It is not same for all combined footing. I have just shown one of the examples so you can get some idea. And you can see in this case that it's stepped. We'll see that both columns are resting on some smaller slab. Their dimension is small compared to the bottom one. So the second one, the bottom one, is with a larger slab. Area is larger. So we do these types of design when we are getting the heavy loads on both the columns. You can see in the case of bridge where the column, so there are heavy loads coming on the column. So in that case, you will see this type of thing. So this is one of the examples. So you can get reinforcement detailing how they are doing, and can get some actual idea of what they are doing. So for the other purpose, when you are getting we are going to design the combined footing, we are going to design the reinforcements. We will see according to the loads and there are various factors, you can get the different shape or different reinforcement detailing also. So there is no issue, right? The third one is the strap or cantilever footing. The strap or cantilever footing consists of two isolated footing connected with a structural strap or a layer or a beam. See, this is not a type of combined footing. This strap or cantilever footing, it's combined two columns, but thus connecting to each other. It does not take any soil erection. We design the strap footing as a rigid beam, but it does not even take the soil erection. So by designing this strap footing, you have not to consider whatever the pressure coming on the soil and like that. So it's just combine the two. You just connect the two isolated footing with each other. So why we go for the strap footing? We will see the strap footing is more economical as compared to combined footing in some cases where the two columns are really apart and their bearing capacity of soil is relatively high. So in that case also we go for the strap footing. We do not go for combined footing, because as compared to the strap footing, that in the two cases where the bearing capacity of soil is relatively high, or where the two columns are really apart. So in that case, you will see the strap or cantilever footing is more economical. You can see in this figure, you can see that there is a two isolated footing are there, and that strap or cantilever footing that's connecting with two isolated footing, right? Or you can see that the first one, the footing with the larger dimension, the second, the footing is the lesser dimension. So that we do, suppose in this column, the first column, the loads are coming on, higher load are coming compared to the second column. So we will design the higher, we will go for the larger, we need to larger distribution area. So that's we go for the, we have to increase the footing area, right? And this strap footing we design for the rigid beam. So you can see in this figure also, you can see there is isolated footing, that column is reinforcement are there only, but yeah, see there is isolated footing, and this one beam is connecting to those isolated footing, and that beam is called strap footing and cantilever footing. So we designed the strap footing in such a way that whatever the line of action coming, it should be passed through the resultant of load. So that's very important. And so whatever we have designed the strap footing in such a way that the both, whatever the line of action passing, it should be same, the resultant of load. Okay. So that our the one of the principle of the footing also. Whatever the center of gravity or whatever the center of gravity of the footing, it should be same for the whatever the load structure, whatever the load on coming on the structure. So all the action pass through the, all line of action pass through the resultant of the footing or center of gravity of the footing, right? So it is one of our the principle or main principle to design the footing. Second figure we have, say, see in this case, in this figure there is also reinforcement detailing. So I just mentioned, so you can get some ideas of how they are reinforcing, how they are providing the steel rod in the strap footing. The next one is mat or raft foundation. So mat or raft foundation is a larger slab which support a number of column or wall. A mat or raft foundation is a larger slab which support a number of column and wall. So we need to design the raft or mat foundation where we have the soil, we have the loose soil or clay type with their bearing capacity are very low, or their pressure, allowable pressure is low. So in that case, we have to go to design, we have to go for the mat or rod foundation. So mat or rod foundation we can design for a whole structure, or we can design also for part of the structure. It depends. So in the city area, you will see there is a when we go to design for the basement. So and we will see there is a we need to space in the basement. So what we do, we just design a larger slab and number of columns is constructed over there. So we can we can get so many empty area. So basement is like that. So we in that case also we can go for the mat or rod foundation. In the case of where the loose soil available, where the bearing capacity of soil is less, so in that case we can go for the mat or rod foundation. In other cases also, where a number of columns are there, a number of walls are there, and their footing are overlap, or they are so close, like they are not touching each other, but they are so close. So better go for the mat or rod foundation. So mat or rod foundation is also very important for the reducing the differential settlement. So differential settlement is basically, suppose there are two columns, there are two footings of the two columns, and the settlement of one footing is more as compared to the other footing. So in a building we call, so that is a case of differential settlement. So by designing the mat or rod foundation, we can reduce the differential settlement. Okay, up to desired factor. So we can reduce the mat or we can reduce the differential settlement. So in that case also, this raft or mat foundation is very, very important. You can see in the figure, there is a raft or mat foundation. So you can see there is a larger slab and a number of columns are constructed over there. So there is a reinforcement detailing in the raft foundation that you can see, and there is a number of columns are not constructed, but you can see there is a number of columns are there. So reinforcement detailing, or you can, by seeing this figure, you can get some idea. So there is a larger slab. The second figure, also you can see there is a slab and number of columns are constructed. So depth of the footing, and that is important to select the depth of the footing. So we have to remove this topsoil. So the footing should be located below the topsoil, consisting of organic matters, which eventually decompose. So there are various factors. By keeping all the factors in mind, we have to select the depth of the footing. Those factors are, first one, the depth of footing, frost depth, zone of soil volume change, adjacent footing and property line, sloping ground, water table, scour depth, underground defects, root holes. So these are all the factors. So see, but it's basically we are designing footing. We are selecting the depth dimension of the footing, like depth, width, length, according to their bearing capacity of soil. And you have designed that footing. Suppose after some time, that bearing capacity of soil is get reduced by some other factor, like I mentioned these factors. So what will happen? So design would be fail. Structure can be fail, right? You can get the excess settlement. You can get the differential settlement. So we have to select depth of the footing by keeping all the factor in mind, so that the bearing capacity what we have taken for design, that would be same, that would be not vary throughout the life of structure, right? So by keeping all these factor in mind, we have to select the depth of the footing. So there is a mention by Rankine. So minimum depth that is mentioned in the IS code 1904 1978. So minimum depth we can keep by using this formula. So where the df is equal to p naught by gamma into 1 minus sine phi divided by 1 plus sine phi the whole square. So where the df is the minimum depth of foundation in meter, p naught is the bearing capacity of soil in kilometer per meter cube, where the gamma is the density of soil or the unit weight of soil in the kilometer per meter cube, phi is the angle of repose of soil or angle of internal friction. So minimum depth you can select. So whatever the minimum depth you will get by this formula, so we will provide some extra depth. Like suppose by using this formula we get the depth of foundation is 1.5 meter. So we will keep 2 meter, right? We will go for the safer side. We will go to the safer side, right? So loading, there are various loads. According to that we design, and whatever the load coming on the column or on footing, so that includes the dead loads. So dead loads is the permanent load of the structure, that is the weight of the material, like weight of the column, weight of the beam, weight of the wall, right, etc. And that is fixed to the structure. So whatever the their volume, what we know the density of that material, like reinforcement, like a plain cement concrete, like wall, like brick, whatever. So we are just calculating that we have the density. So we are calculating the volume by multiplying, we can get the weight. So we can get the dead load. Live load, generally it is the movable load. So in the whole life, in the life, each full life we are using that. So that is mentioned in the IS code 875. So according to that, we can select the live load. So by safer side, what we do, we take half of the live load as a dead load. Right. There is a wind load also. Snow load, weight of unit weight of snow load, usually we take 1 kilonewton per meter square in the cold area. So where there is chances of snowfall, the snow load is coming. Earth pressure. Earth pressure generally apply a lateral load on the structure, so that is also important. Water pressure, earthquake load, that is a very important to do the seismic analysis to get some idea. Combination are also important. That is we can take according to the IS 1904, 1974. So there is a combination, two combination, dead load plus live load. And the second combination is dead load plus live load plus wind load or a seismic load. So either we take seismic load or we do the wind load. So there is a common assumption that wind load and or seismic load do not come at the same time. Will not come at the same time. So there is a common assumption that everyone does. But you can say like, sir, if both load will come at the same time, the structure would be safe because we have not designed for that. But there is a common assumption like to do the economical design for structure to either we take the wind load or we take the seismic load. So if the wind load or seismic load is less than 25% of the dead load or live load, so we can neglect this seismic load, right? Or foundation can be designed for dead load plus live load. There is a first combination. But if the wind load or seismic load is greater than 25% or more than 25% of the dead load plus live load, so foundation would be designed as a second combination. For the second combination, dead load plus live load plus seismic wind load, or dead loads plus live load plus wind load, right? Principle of footing, that is very important. So before actual design, we have to estimate all the loads like dead load, wind load, or other load that I mentioned in the previous slide. And bending moment at the base of the column or wall should be ascertained if it is subjected to eccentric load or moment, right? In this lecture, in this unit, I will discuss that if the load is coming, the eccentric load is coming, so how the pressure are distributing. But if the load are at the eccentric load, due to eccentric load, then some extra load are coming on the structure. Suppose there is a T, and suppose there is a eccentricity E, so other moment will come P into E. So because of that moment, we will see that on the footing side, you will see in one side there is a pressure is less, on the other side pressure is greater. So we have to design that maximum pressure would be less than the bearing capacity of soil. So we have to see in building or in the structure or in footing whether the bending or moment is coming or not, whether the eccentric load are there or not. So we have to be certain for that. Bearing capacity of soil depends upon the depth of the footing, length, and width, right? So, and when you have not select the depth of the footing and length width in a proper way, so it can be not good for the structure, right? So the bearing capacity of soil can be varied, and that would be because already designed, you can select the depth, foundation, length according to the bearing capacity of soil. So we have to be very sure about that. Samples should be taken to determine the engineering property of soil, like bearing capacity of soil. Also, so many other tests we have to do to calculate, to know the bearing engineering property of soil to better design. So footing is designed using the following procedure. So bearing capacity of soil we will determine. Then you can, based on that, we can calculate the dimension of the footing. The fourth one is very important. The factor of safety against the sliding should not be less than 1.5 when the combination of dead load, live load, earth pressure, plus wind load, or 1.75 in the case where the dead load, live load, or earth pressure combination are there. In the overturning cases, we will see the factor of safety should not be less than 1.5 when the combination of dead load, live load, earth pressure, wind load, or in the second case where the factor of safety should be less than 2 in the case of where the dead load, live load, or earth pressure. Proportional is also important for the equal settlement, right? So it is able to proportional to in such a way that they have to be equal pressure under the service load, so that the footing would be settled by equal amounts. So there is chance of differential settlement would be less, right? So that is very important. So dead load from the each column, including the weight of the footing, so we have to determine maximum live load to which each footing subjected to determine ratio of the maximum load to dead load for each footing. We have to determine the footing that has largest live load or dead load ratio is taken to governing footing. So you have to be remember that governing footing, the footing that has largest live load to the dead load ratio is taken as a governing footing. So from governing footing, we decide the area and then pressure we distribute it to all the column or footing, right? We will see. So the area, cross-section area of a governing footing is determined by using this formula. A dead load plus live load divided by allowable bearing capacity. That is coming by testing. That we have fixed by done some testing. Suppose the plate load test or some other test. So we have fixed the allowable bearing capacity of soil. So on the basis of that value, we can calculate the gross cross-section area of a governing footing. So design bearing capacity for all footing. All footing is defined. All footing means except the governing footing. So we can calculate QD by service load for governing footing divided by area. What is the meaning of that? The AG we have fixed for the governing footing, right? And then we are calculating the QD, designing bearing capacity. So area of the other footing is determined. So now by keeping the QD for all the footing, now we can calculate the area for the other footing. Other footing means except the governing footing. So we can calculate area service load for that footing. So AG for the governing footing, AG cross-section area for the governing footing. A is the cross-section area for the other footing except the governing footing, right? Design of footing or design of plain concrete footing, right? So we design the plain concrete footing where the light loads are there and soil is good, their strength are good. So we can go for the designing of plain concrete. But in the case of heavy loads or in case of where the soil is loose soil, so then we can go for the reinforcement footing, plain concrete footing. So the required width we can calculate. So we have the QNA, allowable bearing capacity of soil. So we can calculate the required width. So we will divide load by the QNA. We can get the required width for the unit length, right? So actual pressure we can calculate. See, why we are going to calculate the actual pressure, right? Suppose always what we do that suppose required depth we are getting 4 meter. Suppose we are getting 4 meter. So what we do, we always provide some extra width. To be safer side, we provide the extra width. So we select suppose required depth we have 4 meter, but now we are selecting, we are taking the 4.5 meter. So the actual pressure, the contact pressure will come at the base of the footing, that will be different. That will be not QNA. So that would be less than QNA, right? So we have to calculate. Suppose you have not, we have taken the exact value that whatever you have get required depth you have. So there is no need to calculate the actual pressure. But whenever you have calculated the required width and we have provided some extra width as compared to required depth, so always we have to be calculate the actual pressure. So load is there and provided width. So by taking the ratio, you can get the actual pressure, actual contact pressure at the base of the footing. So there is a codal provision. The thickness at the edge of the footing should be at least 50 centimeter. On cohesive soil, generally a minimum thickness of centimeter is specified in order to resist swelling pressure. In the case of when we are going to select depth of the footing, we have to take care of the block cutting soil, because that soil is very different in nature. Like that can be swell, it can be shrink easily. Suppose you got the water, so it can be swell, or when it will dry, it will shrink. So it will affect the footing, right? So that is very important. So by selecting the depth of footing to take care of the soil is very important. What kind of soil are there? Say 45-degree load distribution also commonly used. It can be vary. You can see in other book you can see different value. You can fill also you can see the different value. But generally we take 45-degree. Reinforcement concrete footing. Already I told you that if the load are high and soil are less in bearing capacity soil, so we can go for this reinforcement concrete footing. So required depth we can calculate by using the same formula, Q by QNA, allowable bearing capacity. QNA is the allowable bearing capacity of soil. You can see in the figure there is a RCC straight footing. So the both outward portion is behave as a cantilever. So cantilever side, the bottom side, the soil pressure is applying outward in a vertical upward direction. So the bottom side, the tension will come, right? So we will provide the reinforcement. We place the steel bar at the bottom side so that it will take the tension. And you can see there is a footing. This is the cross section of footing in column. So there is a column. The load is coming in the column is Q, and the dimension of the column is given B. Suppose it is a spread, then it will be B into B cross section. And maximum bending moment will take at the face of the wall or face of the column. Okay, or for diagonals here, maximum diagonals here, we take as if from the D distance, where the D is the effective depth, right? So there is a reason why we take at the D distance. We'll say there is a crack pattern. So it will be a 45-degree. So suppose D is there, or suppose D depth is there, and we'll take the horizontal distance in horizontal direction. So we'll take 45 degrees. So D to D, D and D. So that's why we take D maximum diagonals here at a D distance from the face of the column. So that are very important. So that in this figure, whatever I mentioned, you can understand by the line diagram. So to better understand, I made the line diagram. So see, there is a footing I mentioned by a line. There is a column. So the pressure, the actual pressure is acting from the base of the footing, that is Q naught. And that Q naught we have calculated by provided bit. So Q by provided bit, by dividing this ratio Q by provided bit, we can calculate the Q naught. So that is the actual pressure, actual contact pressure at the base of the footing. Width of this column is B, small b, and the width of the footing is capital B. So now we are going to calculate the bending moment, that is maximum bending moment at the face of the column, and that is mentioned in the figure by x-axis. And x-axis distance from the outward portion is B minus B by 2. Obviously, by geometry, you can get B minus B by 2. So the critical section, at a critical section x-axis, the maximum bending moment is taken in the face of the monolithic wall. So bending moment at the x-axis will be Q naught. So how we can calculate? Suppose a line diagram, there is a UDL, and we have to we are going to calculate the maximum bending moment. So there is a UDL load. So UDL load into length, and there is the center of gravity of that load. So Q naught, and their length is B minus capital B minus small b divided by 2. So the length of, so for that length, that UDL is acting Q naught, right? And now we are going to multiply with, this is the force. Now we are going to multiply this lever arm. So we have to be multiply with the axis to the, what is the distance between the axis to the center of that load. So center of that load would be B minus B by 4. B minus B by 4, right? So by multiplying, you can get Q naught into B minus B by whole square divided by 8. So that this is the formula that you can apply everywhere when you are getting the calculating the maximum bending moment for a critical axis. For the checking the diagonals here also, the critical section at a distance equal to the effective depth d of the footing from the face of the wall. So see that I've mentioned in the figure by x1 axis. So the distance of x1 axis from the outside. So that would be b minus b by 2 minus d, right? Because we have to calculate it at a d distance. So b minus b divided by 2 minus d would be the distance of x1 axis from the outside, from the edge of the footing. So we are calculating the shear, means we are calculating the shear force. So whatever the shear force will be at the x1 axis, that will be the diagonal shear, and that will be the critical shear. So what we have to do, we have to just multiply the distance with the UDL loading, right? So Q naught into P minus B by 2 minus D. So that will give us the diagonal shear. Are you getting my point? We have calculated the maximum bending moment at the face of the column. We have calculated the diagonal shear at a d distance from the face of the column. So let us solve a numerical. So you can get more idea. So design a reinforcement cement concrete footing for a 1 meter wide concrete wall carrying a load of 800 kilonewton per meter or per minute unit run. The allowable pressure is 200 kilonewton per meter square. And then in the question it's saying that take the D, that is effective depth, is 0.52 meter. Meter is not mentioned, but yeah, meter. So D is 0.52 meter. So again, I meant at the line diagram. So you can see the depth of the width of the column is given, width of the wall. Here it is the wall, not column, right? So width of the wall is given 1 meter. And the carrying load is given 800 kilonewton per meter. C, so the pressure at the base of the footing. So suppose capital B is the width of the footing. So whatever the pressure at the base of footing should be less than or equal to 200. That is allowable side pressure, right? So we can calculate. So B will be greater than equal to 800 by 200, greater than equal to 4 meter, right? So to be safer side, we are assuming 4.5 meters. So we have provided 4.5 meter, right? But it is required only 4 meter, right? But we are providing the 4.5 meter to be safer side, right? So actual pressure now we have to calculate. Already I told you, whenever we are changing the we are providing more extra weight, so we have to be calculate actual pressure or actual contact pressure at the base of the footing. So actual pressure at the base of the footing would be 800 divided 4.5. That will come 178 kilonewton per meter square, and that is less than equal to 200. That is less than equal to 200, right? It will be not greater than equal to, right? So it would be less than equal to 200. That is safe, right? You can correct. That is safe. So see, now actual pressure we have 178, that is coming at the that are acting at the base of the footing in upward direction. So now we have fixed the x-axis, and their distance from the outside is from the edge of the footing is 1.75 meter. We can calculate by taking the P minus B by 2, and there is x1 axis at a d distance, and d is given 0.52. So you can calculate the distance x1 axis from the edge of the footing, that you can get 1.23 meter. You have to calculate that. You will get the same value. Okay. So width we have provided 4.5 meter. So bending moment, maximum bending moment per unit run or per minute per meter, you can calculate. So we have this formula Q naught we have 178. Capital B we have 4.5 meter, small b we have 1 meter. So we get the 272 kilonewton meter per meter. Per meter is the this saying for the bending moment for 1 meter of wide of wall per meter run, you can say. So diagonal shear also we can calculate for the x1 axis. So we have this formula Q naught into B minus B divided by 2 minus D. So we have the Q naught. See, in this case, Q net, it won't be 200, right? Because Q net is the actual contact pressure at the base of the footing. Connect 200. 200 is allowable soil pressure. Suppose if you will provide the 4 meter width. So that in that case, Q net will be 200. But we have to be safer side, we have provided some extra width, right? So then we have calculated the actual pressure. So that 178 pressure kilonewton per meter square, that pressure is at the base of the footing. That is not a 200, right? That is capacity of soil. So it can resist up to 200 kilonewton per meter square pressure. So we have to calculate the diagonal shear, that is 218.94, 218.94 kilonewton. So see, we have to calculate on this value also. So in the geotechnical, for the geotechnical engineering point of view, we have to do this much only. We have to calculate the dimension only. Suppose you are designing the foundation, then on the basis of this maximum bending moment, we have to calculate the reinforcement. We have to calculate the effective depth, whether it's safe or not. We have to design the concrete, right? So there is various procedure we have to do from this only, but from the geotechnical point of view, we have to do this much only, right? These are the solutions that I have taken. Thank you. In the next lecture, I'm going to discuss the different footing for the. We have to discuss the design of the footing for the isolated, for the combined, for the rectangular combined footing, for the trapezoidal combined footing. So you will see. Thank you.